I can succeed at recording this class. It's been a day, let me tell you. Homework questions to start. Anything for homework questions? Stuart, I have to get my book. Yes.
It's not on particular homework. I was just confused when I was looking back at my notes with how to multiply BA.
Yes.
So I understood how to do AB, but with
Yes.
BA, I was just confused with that. Is that where you do the inverse of it?
So just, here's my snarky answer. Relabel your matrices and then do the exact same thing that we did. Like you just multiply them in the opposite order.
Oh,
that's it.
Really?
That's my snarky answer.
So like A turns into B and then B turns into A essentially?
You can do it that way, yeah. And then you multiply it the exact same way. Yes.
Okay.
Yeah. It's just, the point is that matrix multiplication is not commutative. So you got to be careful in what order you write down the matrices. If you write one on the left, this is my left, I don't know if it's your left or not, left, and one on the right, and you multiply, then you might get a different answer if you flip these around and multiply. So
okay.
You also have to be careful with the dimensions because sometimes it'll work to multiply in this order, but it won't work if you flip them around. So I'm pretty sure they have to be square in order to multiply them in both directions. So.
Got it.
Cool. Other homework questions? Other ones, other people, other homework questions. What else we got? No, good, happy, we're good. Okay, reminders then, because it's Monday and we do reminders, well, pretty much every day, but reminders. So homework is due Friday, right? Friday, give me a thumbs up. Friday is correct. Yes, Friday. Okay, cool. From 5.1, 5.2, and 5.3. 2 homework assignments left. That's it. That one and the one from 5.4 and 5.6. That's the first thing. Second thing, 8 class periods left. That is all, plus the final exam. Again, I love you all, but I'm ready to be done with this. So we can make it. 8 more class periods. Final exam, Wednesday, May 13th at 10:30. That's our normal exam time. That's when it was scheduled for. So it should not conflict with anything else that is happening during finals week. Wednesday, May 13th at 10:30. We should be doing it, I expect to do it the same way that we did the first test. Everybody turn on video, take it that way, etc. If you have issues with that, please feel free to let me know. But it worked decently, I think, for the first test. Yes, we're getting nods, that's good, okay. So we'll do it that way for this test again. I think that it's going to be cumulative, but, now there's loud noises, sorry, I don't know what's going on with my water. I think that it's going to be cumulative, but I also think that it will probably focus more on chapter 5 than I do normally for a final exam. My goal for this week is to map that out. So I will hopefully have a better answer for you by the end of this week as to what is going to show up on the final exam. All right. Also, I don't think that I'm going to write it to take an hour and 45 minutes. I'll write it to be longer than a regular test, but probably not as long as a regular final exam. So my best guess would be an hour to an hour and 15 minutes. So that still lets you have time at the end for uploading. It gives us some time at the beginning for me to post it on Moodle, walk through stuff, etc. So that's my tentative plan, an hour to an hour and 15 minutes. So a little bit longer than a regular test, but not super, super long. Questions, questions on those logistics? Anything there? Okay. The last 2 days of the semester are review group work, and that fits into the final exam is going to be cumulative. So I'll probably keep a problem from chapter 3 on the review group work just because it would be good for you to see one more time. I will decide for sure if I'm putting a problem from chapter 3 on the exam, and I will let you know that ahead of time, I promise. But that's the last 2 days of the semester. So again, it's up to you. I'll do half of the group work on that last Wednesday and half of the group work on that last Friday. You can decide whether you want to work live on Zoom. That did work well last time, so I'm happy to pop around to breakout rooms, etc. However you want to do it. I personally think that you got the time scheduled for class anyway. You might as well spend an hour and be productive. But it is up to you, and I am not going to mandate or dictate that. So your call. I think that's all the reminders that I have. Anything else before we get into content? Anybody, anything? Okay then. So we talked a lot about matrices last time, right? And that was good and beneficial, and hopefully even if you haven't had linear algebra, you are relatively comfortable with the basics of matrices right now. So today we're going to get back to differential equations. This is a differential equations class as opposed to being a linear algebra class, and so we're going to get back to how are we going to use all this stuff to solve differential equations. So if we have a first order system of equations, first order means that we only have first derivatives, right? That's the highest derivative that appears. First order, we know what systems of equations mean. There are a ton of different ways that we can write this. We can rearrange, we can write this however we want. Here's how we're going to write it today and a little bit moving forward in order to make it easier to deal with matrices. So we're gonna say x1 prime equals p1 of t times x1, p12 of t x2 plus a bunch of dots, p sub 1 n of t xn plus f1 of t. That's our first equation. We'll talk about what all those letters mean in just a minute, but that's our first equation here. So x1 prime equals p11 of t times x1 plus p12 of t times x2, a bunch of dots, p1n of t xn plus f1 of t. We'll do one more line and then we'll do some dots. So x2 prime equals p21 of t x1 plus p22 of t x2 plus a bunch of dots, p2n of t xn plus f2 of t. Okay, and then we'll go all the way down. We're going to assume that this is a square system, and we'll talk why we want to assume that when we get to actually solving these things. But we're going to go down to xn1 prime equals pn1 of t x1 plus pn2 of t x2 plus a bunch of dots, pnn of t xn plus fn of t. So again, there are 800 ways to write a linear first order system of equations. This is the one that we are going to be using to get into solving it with matrices. A solution. Remember that a solution is functions for all of your dependent variables, right? Our independent variable is t, and then in this case, we have n dependent variables that we need solutions for. So our solution is going to be x1 of t, x2 of t, all the way through xn of t, Or if we want, we can just say x1, x2, all the way through xn. So that's what our solution is going to look like. That's what we're trying to find, okay? When we did examples with just two of these, our solution was x equals and y equals, right? Another way of saying that would be x1 equals and x2 equals. So that would be another way of saying this. I'm saying x1 through xn. And this is homogeneous if all of the f sub I of t's equals 0. So if f sub I of t equals 0, for I equals 1, 2, all the way through n. You can kind of sort of see that, right? Remember, homogeneous has a 0 on one side of the equation, so we could move all the x sub 1, x sub 2, x sub n over to the other side of the equation, and then we would have a 0. That's what this would look like. Okay, this is a disaster. This is ugly and messy and yucky, and we spent a day on matrices so that we could write this better. So here's the better. Here's how we're going to write this. Here's my better. My better is going to be introducing a couple things first. P of t, that's capital P. This is the coefficient matrix. And this is going to be P sub ij of t. Remember that notation, right? That's our generic notation for an entry in the matrix. So this is for I equals 1 to n and for j equals 1 to n. So we can put all of those coefficients, their functions maybe, but all of those coefficients into a matrix. We are going to have, there's no good way to say this, so a right-hand side column vector. So this is going to be, when we do vectors, we put an arrow over them. So f of t, you can also do it in bold, but that is harder for me to do when I am teaching and writing. So this is going to be f1 of t, f2 of t, all the way going down to fn of t. I know those technically aren't on the right-hand side or aren't by themselves on the right-hand side because of the way we wrote this, but normally they would be, and you can imagine them being on the right-hand side. So that's why we're calling this the right-hand side column vector. And then the last thing is a solution vector. This is going to be x, and again, this is a vector, so we're going to put a vector arrow over it, vector arrow with x, and this is just going to be all our solutions. We're going to put them in a column vector. So it's going to be x1 of t, x2 of t, all the way down to xn of t. Or again, sometimes we write it without the t's, x1, x2, all the way down through xn. So that's going to be our solution vector. Our goal is to find a solution vector because we said we want to find a solution to the differential equation. So our goal is to find a solution vector. With all of that notation, here's how we can write the system in a much cleaner way. So our system of equations turns into this. Left-hand side is that solution vector x, but it's the derivative, right? So left-hand side is x prime. Tell me we're seeing that. Give me a thumbs up. Yes, x prime on the left-hand side. Right side, I am going to have that coefficient matrix times my vector x. And you can see that if you multiply out those matrices, it'll end up working out. So P of t times that vector x. And then I have to add that right-hand side vector, so plus f prime of t. That's way better. That's way better because then we cannot have to write out the plus dot 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 and all of this stuff, and we can use matrix properties in order to hopefully solve this system of equations. Okay, that's a good place to pause, be able to see all of you again. Questions at this point? Anybody, anything, questions at this point? Stuart, yes.
Right at the end, you said plus f prime of t. Is
Oh,
that
F,
called
I'm sorry. I said it. F. Sorry, F. Should be F. Thank you.
how do you talk about it? Vector f?
Vector F. Yeah, you can say
Okay.
vector F, or you can just say F and write the vector arrow over it. Either way.
Okay.
Yes. Other questions? Okay, then, do you remember how we did this way back at the beginning of the semester? Like way back at the beginning of the semester. We came up with a system, or one equation, right? We came up with an equation. We said, oh, look, here's a solution by magic, completely by magic. Can you verify that this is a solution by magic? And then if I give you enough solutions, can you find a general solution? Tell me you remember some of those, hopefully the magic, if nothing else. People are sort of kind of nodding at me. Okay, that is the same process that we are going to go through for systems of equations. So here's what we're going to do, and we're going to do some magic. Again, stuff is going to appear by magic. So given a system of equations, here's what we want to do. First of all, write it in matrix form. So we want to do that. We want to write it in matrix form. Secondly, verify that a solution appearing by magic is actually a solution. And so I'm going to yell at you a lot about starting on one side and working your way to the other side. You've missed me yelling at you about that. I know you have. Verify that the solution appearing by magic is actually a solution. Third, we want to use solutions. Again, appearing by magic, I should say particular solutions. Use particular solutions appearing by magic to create a general solution. So we want to use particular solutions that are appearing by magic to create a general solution. And there's a catch here a little bit. Do you remember when we did this back in chapter 2, there was a requirement. Your particular solutions had to have a certain quality in order to be able to use them to create a general solution. Do you remember what that particular quality was? They had to be what? Anybody, anything? The particular quality, I'm going to be able to, I want to see all of you. The particular quality that your particular solutions had to have in order to be able to combine them to a general solution. Bethany.
Was it like linearly independent?
Yes, they had to be linearly independent. So that is going to be something underneath this one as well. So 3A is going to be check if particular solutions are linearly independent. Do we remember how to check if particular solutions are linearly independent? What was the fancy thing that we created to check if particular solutions are linearly independent? I can't see all of you now. You'll have to do a virtual hand raise. The fancy thing, Stuart, we used the...
Was that the thing where we did like cornrows and then
Yes.
It has like equal 0?
Yes, is or is not equal to 0. Do you remember the fancy name of that thing that we created? Anybody? Okay, we're now indicating what needs to get studied for the final exam. That's called the Wronskian. Do we remember the Wronskian? Oh, sorry, I just said it before someone. Wronskian, thank you, Aiden. Lovely, Wronskian. Okay, so using the Wronskian, And you even spelled it right. Nicely done. Using the Wronskian. And then what we want to do, and this is our ultimate goal, is find particular solutions. So not rely on magic. Find particular solutions. And this, by the way, is, I should have said this at the beginning, this is given a homogeneous system of equations. If we are working with a homogeneous system. Remember back in chapter 2 also, we totally worked with a homogeneous system, and then we said, okay, let's jump to non-homogeneous, but we did homogeneous first. Okay, so those are our goals. That's what we're looking to do.